So let us go back to whatever has been bothering all of us. So what we are essentially choosing when we did regression here was we are going to make sure that the output is either 1 or 0, right, and then we are trying to regress on that, right. So what do you want our function to do? Basically you want your f of x to give you probability of k given x, right, but then trying to do that is a little harder. So what we are going to do is we are going to look at some kind of a transformation of the probability, and we are going to try and fit that. Okay. I'm going to look at the logit transformation, which is essentially log of right. So if you think of p of x and 1 minus p of x, the probability that x is okay, let me put it this way. To make my life easier for the next few minutes, I am going to assume we are dealing with binary classification. Okay. So the class labels is either 0 or 1, okay, and p of x is essentially okay. So when I say p of x, it is essentially probability that the output is 1 given the input is x, okay. So this makes my life a little easier while I write the next part. So given that p of x is the probability it is 1, what is 1 minus p of x? Probability 0, we are talking about binary classes, right. So this is sometimes called the, this is, you know what the probability of success divided by the probability of failure? Odds, right. So this is sometimes called the log odds function, okay, or the logit function, okay. So this is essentially the transformation that we want to look at. So what I am going to do is I am going to try and use that. Okay, right. I am going to try and fit a linear model to the log odds. Okay. So what is p of x in this case? Right. So what is this function going to look like? That is a sigmoid, right. So essentially we are saying that my probability of x is going to be given by a probability that x is 1 will be given by a sigmoid, right. Term in the, it's not visible. Is a term in this power visible? Beta x. Is this term visible? Okay, that is the term in the power. Okay. Except that here it is a minus before that. Okay, everyone got that? Other room things are visible? Yeah, because they are probably zooming in on this, right? Okay, fine. Great. So what do we have here? So what we do if p of x is greater than 0.5, we will output as 1. P of x is less than 0.5, we will output it as 0, right. So is it okay? Because see, even though I am doing linear regression and linear regression is unbounded, right, I am going to plug it into this expression, and therefore this will make sure that my probability is between 0 and 1, right. Right. What is that point? That is 0.5. Depends on what I put for my beta naught, right? Yeah. Huh? So if my beta naught is 0, then that will be 0, right? Minus beta naught. Yeah. Yeah. So what about the classifier that I am learning here? What about the separating surface, the decision boundary between class 1 and class 2? What did he say? Huh? What is that? It is complicated. Okay. Think. Huh? P of x equal to 0.5, but what does it look at the expression that we have here, right? So when P of x equal to 0.5, what will this be? 1. P of x equal to 0.5 will be 1, log of that will be 0. So essentially the thing is beta naught plus beta x equal to 0, right, that is a straight line. I mean assuming x is unidimensional, that is a straight line, right. So even though I did something that looks complicated, okay, I used an exponential to define my probability, the decision surface turns out to be still a hyperplane, right. So plug in P of x equal to 0.5 here, so I am going to get 0 on the left hand side. I am essentially solving beta naught plus beta x equal to 0, right, that is just a straight line, right? Assuming that, yeah, okay, that is a hyperplane. Maybe I should do the whole class in one dimension, that makes it easier for people to visualize things. Anyway, right. So one thing I should point out is that logistic regression looks simple, right, but it yields a very powerful classifier, okay, it works very well in practice, and it is used for not just for building classification surfaces, okay, but it is also used a lot in what people sometimes call sensitivity analysis, right. So they look at how each factor contributes to the output, right. So how much is each factor important in predicting the class label. So for doing that they do logistic regression, and then they look at the beta vector and figure out how much each variable is going to be contributing to the output, right. So people use that a lot. I mean of course you can use anything that we have seen for doing this kind of sensitivity analysis, I am just telling you what people use in practice, okay. So logistic regression is something that is used very widely in practice, both by machine learning folks and by statisticians. In fact when I worked with a few doctors, right, it was almost impossible to get them to accept anything else other than logistic regression as a valid classifier, right, because they were so sold on logistic regression, and with good reason, because it does work very well in practice, right. Okay, so that is for 2 classes. So what do you do for multiple classes? So multiple classes I am essentially going to take recourse to this form, right. I am going to say, okay, the probability that the output is class 1 given x is given by an expression like this, okay, the probability that the output is class 2 given the input is x, is given by another expression like this, where which will have a different set of beta naught and betas, right. Likewise for every class I am going to say it is given by a different set of beta naught and beta. So do I have to do that for all the k classes? I have to do it only for k minus 1 classes, because the kth class probability will be automatically determined, right. So I will have to have k minus 1 sets of beta if I have k classes, right. I have to figure out how to estimate those. Thanks. So we are going to write like this for the k minus 1 classes. By convention, either the first class or the last class, whichever arbitrary numbering you choose, either the first class or the last class, the coefficient are set to 0. Setting the coefficient to 0 will essentially give you the answer that you want, right. Sorry. Sorry, I'm really sorry, I messed up. So this is the expression that you want, right. So for every class k, the numerator will have just that class's variables, and the denominator is going to have all of it, okay. So now you agree with me, setting it to 0 is fine. Yeah. Okay. So how do we estimate the parameters for logistic regression? So it's a little tricky, since we are anyway trying to model directly the probabilities, right. So what we are going to try and do is maximize the likelihood, okay, of the data. So far we have always looked at some kind of error function, and we have been trying to optimize the error function. Whether it was linear regression, we looked at squared error, and then we did the optimization and so on and so forth. But here we are going to look at a slightly different criterion. We are going to optimize the likelihood of the data. So just to keep it together, I am going to do this today, but I have a whole session planned on maximum likelihood and other ways of estimating parameters. So when we come to that, I will do maximum likelihood in more detail in a generic form, right. So right now I will just look at logistic regression and maximum likelihood. So what is likelihood? Suppose I have some training data D, okay, the training data has been given to me, some training data D. So the probability of D given some parameters theta, okay, the probability of D given parameters theta is known as the likelihood of D or theta, theta, okay. So D is fixed, right. Think about it, I am given a training data D, D is fixed. What is it that I am actually looking to find? Theta, right. So this I will write as likelihood of theta, okay. So we are always used to thinking of something that comes after the slash as the conditioning variable and the one that comes before the slash as the actual argument. In this case it turns out that theta is the argument, okay. The probability of D given theta is the likelihood of theta, right, makes sense, right. D is fixed, I am really trying to find what theta is, correct. So finding the likelihood of theta, so the scoring function should be on theta, okay. Does it make sense, right? And I am usually interested in the log of theta, because it allows me to simplify a lot of the distributions that I will be considering, and we will denote this by lowercase l mostly. Okay. So what is the likelihood? So in our case theta is our betas, right. So my input, my D is going to consist of right, and D is going to consist of pairs of data points like this, right. So X is the input, G is the output. We are talking about classification. So G is the output, X is the input, right. So what is the likelihood? So I wanted to stay in the 2 class domain for a while. So G is either okay, G belongs to 0 or 1. So 0 means it's class 0, 1 means it's class 1. Okay. This is a funky expression written. We will come back to this. We will see this again. So this is the probability of one pair xg occurring. Okay. So what is this? This is the probability that x has the label 1. This is the probability that x has the label 0. Okay. And what is this? This is the actual label of this is the actual label of x. Right. If the actual label of x is 1, then this term will appear in the equation. If the actual label of x is 0, then that term will appear in the equation, this will become 1, right. So if the actual label of x is 1, what should be the probability? Probability that x equal to 1, right, that is what I should be looking at. So that is what this is. If the actual label is 0, then I should be looking at the probability that x is 0, that is what this term is, right. So you can see that this gives me the probability of one xg pair, right. I do this for all of them, assuming that they are all sampled independently, right. So because I am assuming they are independent, I can take the product. Okay. So now we know why we love logarithms, right. People who can't see the board see the TV, right. Right. So that is the expression, right. That is simple enough. So now comes the interesting part. We want to do what? We want to maximize likelihood, right. So we need to take the derivative of this and equate it to 0. It is fine, right, because log is a monotone transformation. We can take the derivative of the log, right, equate it to 0 and then solve for beta. Unfortunately, life is not so simple. Right. Okay, let's try and do the simplification. right. So I am multiplying this out and gathering the terms, okay, right. I am multiplying this out, I have gathered the terms here, and we know what that is. What is that? Right, we already know that, so that we can insert that and simplify that there. And what about this guy? 1 minus this, right. I can again write it in a simpler form, right. Log of 1 minus that will give me okay. So now I can take a derivative of that with respect to beta and equate it to 0. What do I get? Right. So take the derivative of this term, right. You are going to end up with minus p, right. So this will go down, right, and I will get e power beta naught with beta x as the in the numerator, right. I will get minus p times x. Since I am doing it with respect to a specific beta j, I will get xij, right. Does it make sense? So this first term I will get minus p times xij, and this one if I if I take the derivative of that I will get gi times xij, right. So that is essentially what I have done here, right. Looks like a nice and easy expression to solve, but unfortunately it is not so, because this one is an exponential function here. So it is not really easy to solve this, right. You have to look at some other iterative method for solving this, and the most popular method used is Newton-Raphson. I am not going to go into the depths of Newton-Raphson, right. People are more interested, you can look it up, but the basic idea is that so if people, if you are more comfortable looking at it this way, so take the old estimate of your value or take your old solution, okay, and look at the first derivative of the function that you are maximizing, right, L prime divided by L double prime, okay. So you adjust this by that, okay. So that is essentially the basic idea behind Newton-Raphson method. I am just defining some terms here. So X is going to be my n cross p plus 1 matrix as usual, right. My P is going to be a vector where each entry is going to be the probability of Xi. So what will be the dimensionality of P? N, right. So it is a n vector that tells me what is the probability of each Xi being 1, right. So that is P, and W is going to be a diagonal matrix where each diagonal entry is P into 1 minus P, right, for that particular data point Xi. So this makes it convenient to rewrite things, and I am going to assume that G, right, is the vector of outputs like zeros and ones, okay, depending on what class it is. So I can write my dou L as what? You know what dou L by dou beta is? It is actually G minus P into X, right, in terms of the matrices. Right, so P is this vector, Y is the vectors of zeros and ones corresponding to the class label, right, and X is my input, right. So I have just basically written this in vector notation, right. So we already found the derivative, I have just rewritten it in vector notation. Does it make sense? Okay. So what about the second derivative? Right. So I am okay. So I am not going to work it out, but it is X transpose Wx, okay, and so W is essentially the diagonal matrix with these entries, okay. So that is my second order, my second derivative. So what do I get now putting this together? It is beginning to look something like regression here, right. You are getting your X transpose, X inverse, X transpose and all that. So we just have to do a little bit more work, little bit of algebra to make it look more like regression, okay. So that is what we will do now. I have just substituted this the derivatives here, okay, nothing fancy. Yeah. So, okay. So we want to solve this problem, right? This is what we really want to solve. We want to solve when this becomes 0, right? So you can see the beta in here, right? No? Yes. The beta is in the P, right? So so I have erased the P off now, but so beta is in the P, right? The P is e power beta naught plus beta x plus divided by 1 plus e power beta naught plus beta 6. So beta is here. I really want to solve for this, right? I want to find the 0 of this function, right? But it is not easy to do because of the fact that we have an exponential in there, right? So what we have to do is look at some kind of iterative method for solving this problem, right? So what the way we do this iterative approaches, you start off with a guess called beta old, okay, and then you do some computation, you get a new guess called beta new, right? So one very popular way of doing this kind of iterative thing is to do gradient following. Have you looked at that? I mean, you might have come across that. This is aside. So suppose I have a function like this, right? I am here. This is my current solution, right? This is, I will call this x old. Okay. So now I will compute the gradient here, right, and I will move in the opposite direction of the gradient to find the minimum, right. So, instead of going all the way I can go a small step, that gives me the x nu, right. So, normally what you will do is you will find the gradient, try to equate it to 0 and get it, but you can do this in iterative fashion also, right, you can take small steps in the direction of the gradient. So, likewise what we are going to do is we will start off with beta old, which is some guess for this, okay. In fact, betas of all 0 actually works fine, okay. I can start off by saying all my betas are 0, okay, and then try to find the beta nu. So, what I will essentially be doing is I will find, so beta 0 will put me somewhere here on the L function, right. I will find out what is the first order and the second order derivatives at this point with respect to beta, and then use that for changing my beta values. Okay. I mean, right. So, people agree with me. So, this is x transpose wx inverse, if you take the product here this will be x transpose wx, so that is just the identity, right, and I take the product here I will get x transpose wx inverse x transpose back, this is w inverse and w will get cancelled out, right. So, I have just done some algebra to get it this way. Think about it, what is x beta old? So, original, I mean it is like linear regression, right. So, it is like the original response I will get if beta old is my variables and I am actually making a linear prediction based on x, right. So, the x beta old is this, right, and I am essentially adjusting it using this quantity, right. So, this is the prediction I make with my old parameters, this is some kind of a adjustment I am making to the prediction. So, this is called the adjusted response, right, and this turns out to be the solution of something known as weighted linear regression, right. So, in weighted linear regression essentially what you do right. So, in linear regression that is what you are trying to minimize, right, that is a squared error, right. So, linear regression this is what you are trying to minimize. Weighted linear regression you essentially have a weighting term in your error function, right. Since I am just saying I am going to minimize a squared error, for every term in the squared error I am going to assign a different weight, right. So, for some data points I want to be more aggressive in minimizing the error, for some data point I want to be less aggressive. So, data points in which I have to be more aggressive I will have a higher weight, for data points for which I want to be less aggressive I will have a lower weight. So, that will allow me to trade off the importance of data points, this is the idea behind weighted linear regression, right. So, this is essentially weighted linear regression. So, the minimizer of this, right, is this, right. Okay, you can do the usual, now you can take the derivative, set it to 0 and solve it, this is easy enough to solve, this is actual linear regression, right. So, the minimizer is x transpose w x inverse x transpose w into z, right. So, essentially what we are saying is your beta So beta nu is essentially solving a weighted linear regression or weighted least squares problem. Okay, you are solving a weighted least squares problem with this adjusted response. Okay, so this is called iterative reweighted least squares. This is a separate algorithm called iterative reweighted least squares for solving logistic regression, but all it does is essentially does Newton-Raphson. Okay. Essentially is doing Newton-Raphson, but the way the iterative reweighted least squares is described to you is, okay, start off with a guess for beta, okay, form the adjusted response. Okay. So as soon as I guess, as soon as I have a value for beta, I can find out what my p is. Okay. So g is given to me already in the data, and my w can be constructed once I know p. Right. I make a guess for beta, I construct my p, I construct my w, okay, form this adjusted response, solve this weighted least squares problem, get a new beta. Okay. Keep repeating this until my predictions are accurate enough. Okay. So that is basically this. This is it's the most popular way of solving logistic regression, but there are many other ways people have come up with, more efficient ways of solving logistic regression actually. And but if you pick up any popular package like R or something, so IRLS is the base logistic regression solver that would be implemented. Okay. So this just to give you a flavor of how hard it can be to optimize things sometimes.